All right, so I trust you were able to do this fine. All right, so the first thing I do is I try to write down the chain rule that I'm about to use, okay? It just makes it simpler, you know, because then you can just plug in every part and you will get your answer. All right, so this is case one, in case you didn't realize that, because you only have, you know, t as your parameter here. We don't have two parameters. Okay, so what's partial of f with respect to x? That's 3x squared y plus nothing. This goes away, right? And how about dx dt? Dx dt is simply 2, okay? And I'm just differentiating this with respect to x, with respect to t. Plus, and then you have the partial of f with respect to y. That's x cubed plus 2y, and I'd better have the parentheses, and then multiply that by dy dt. The derivative of this with respect to t is 4t cubed. Okay, and now that is a correct answer, but remember I said do not use x or y, and that's sort of typical. As I said, it's a standard procedure to rewrite x with this and y like this. So it's 2t plus 3 quantity squared times y, which is t to the fourth. Let's go ahead and multiply this 2 with the initial 3, and that makes it 6. And then this is tricky, right? This is 2t plus 3 cubed plus 2y inside of parentheses times 4t cubed. So it is not the previous answer, but that's your answer. Okay, so it's not difficult, right? Let's use another example here. This time I'm going to give you a function of 3 variables, x, y cubed plus z squared. Oh, by the way, I should say, if if you plug in these things, okay, if you plug in 2t plus 3 and for x, and then y is equal to t to the fourth in this equation, you can write f as entirely of a function of t, right? That will take you some time because you have to multiply this 3 times, cube it, and that's not a simple thing. But once you do that, you can write f as a function of t, and then you can simply differentiate it. And of course, you will get the same answer. It will not be as complicated as this. But again, we are practicing the chain rules. And sometimes, by the way, you can do a simple substitution like that. So it is important for you to know the chain rules. Okay, all right. For this one here, let's say x is, here, I'm going to write down the answers, questions here. X is 2t, y is 3t minus plus u, and z is 4u. Now notice here, I have f, which is my w, and then you have x, y, and z. So x has t, y has t and u, and z has u, right? So in this very bottom level, I really have u and t. I know that some of, like x does not depend on u and z does not depend on t, but it's important to know that I have u and t both at the very bottom level parameter, okay? And here the question, I'm just posing this question. You can answer other questions here. Let's find the partial of f with respect to t, okay? Now I could have easily said find the partial of f with respect to s or u, not s, u, but I'm just picking one of those questions here, one of the 2 questions I can ask here. All right, so this is the situation, I think, case number 3, which is more general because you have 3 variables. This is what you're looking for, right? As I said before, I normally, okay, and I highly recommend you do the same thing. I normally write down the chain rule, the version of chain rule I am about to use. This is a partial of f with respect to x, and then xt plus the partial of f with respect to y, yt plus, remember you have 3 variables for f. So the partial of f with respect to z, and then zt, that's what we are looking for. Partial of f with respect to x, if you're looking at this, is y cubed. That's it, right? X with respect to t, where is my x? Here, right? So that's 2. And then the partial of f with respect to y is 3xy squared. And of course, the z squared term goes away. The partial y with respect to t is 3. And then finally, the partial of f with respect to z is 2z, and then multiply that by the partial of z with respect to t. Well, z has no t, so that's 0. Okay, so this actually is, let's simplify this, 2y cubed plus 9xy squared. Okay, now again, I don't want to have the x or y or z in my final answer, so I would replace y with 3t plus u, and then x as 2t, y with 3t plus u squared. It's not pretty, and you don't really have to simplify this. I mean, I know you can multiply this out. It's going to have 4 terms. This will have 3 terms, but that's not really necessary. Okay, you can leave your answer this way, and you have no problem here. All right, so the chain rules, now that you have multiple chain rules, okay, but the chain rules are not that difficult, right? So that is a good thing. Go ahead and practice on your homework. Right? Now, the last part of this section has to do with, some of you really despise this. There is no reason to despise this. I hope that maybe a hatred toward implicit differentiation will go away after this one, implicit differentiation. Maybe the way you learned it, maybe it's not, that fun, but implicit differentiation is a glorious thing, okay? And I mean like wonderful, right? And some of you may not appreciate this yet. Here, okay, let me tell you how you should appreciate this. This is awesome, okay? You know that the natural log of x, the derivative of the natural log of x, ln of x, is the most incredible function, right? You wouldn't expect log base e, that strange, weird number, which happens to be my favorite number, but you wouldn't expect the derivative of a logarithm with base e, the irrational number, to be 1 over x, but it is. Okay, so this is one of the most surprising results in the whole world of mathematics, which makes e somewhat of a mysterious number, somewhat of a glorious number, a universal constant for sure. But anyway, so this is true. And you can prove this, okay? You can prove this without depending on the exponential function. Having known this, okay? Having known this, what is the derivative of e to the x? Okay, so I know you know the answer. Yeah, this is another glorious result of mathematics. But if you prove this first, which I do in my calculus class, I prove this first using the limits and all the manipulations of limits as h goes to infinity or something. Having done this, you know what this is? This is something you can easily calculate using implicit differentiation, because what we have is y is e to the x, right? You know how to write this using log? Yeah, you can say x is log of y. That's the same thing, right? If you translate that. And then you take the derivative of both sides. And this is the implicit differentiation, right? In implicit differentiation, you think of y as a function of x. So x becomes 1. And this side, if you implicitly differentiate ln of y, thinking of y as a function of x, this is 1 over y times the derivative of y, right? Remember, this is the key thing about implicit differentiation. Whenever you take the derivative of something that involves y, you have to put that y prime at the end because of the chain rule. Okay, guess what this says? This says y prime is equal to y, all right? So that means the derivative of this function, e to the x, is the function itself. Look, it took like 1 minute to prove this part using implicit differentiation, okay, once you prove this. So implicit differentiation is a very, very powerful tool, okay? You should love this thing. I mean, this is so elegant, okay? You should just look at this for like a minute and stop crying. Okay, this is so good. All right, now implicit differentiation. Let's think about implicit differentiation, right? So if you are looking for, let's say you're looking for a, oh, this is too easy. Okay, let's try something like this. All right. And I have an ellipse like this, right? Okay, I'm not going to do that, this one here. Let's say I have an ellipse which is not centered at the origin, okay? And I'm not going to go into all the details here, but this ellipse can be written as x squared plus 3y squared plus 4y is equal to 8. You can graph this and verify that this will give you an ellipse. In fact, if you complete the square, okay, if you complete the square, you will be able to figure out what the center is and what the semi-major and semi-minor axes are. I'm not going to do that, right? Let's just assume, which is true, let's assume that this equation gives you this ellipse, okay? Again, by completing the square. You know that the center has the, because x squared doesn't appear anywhere else, the center has to be on the y-axis and so on. All right, now this ellipse goes through the point 1, 1. Okay, plug in 1 here, 1 here, 1 here, and you will see 8, right? So this 0.11 clearly belongs to this ellipse because it satisfies the equation. What is the slope at this point, 1, 1? Okay, and of course it's going to be negative. You can tell from the picture because the line is going to be something like this, right? That's a tangent line. Didn't come out very clearly. Maybe I should do it again. Yeah, that is a tangent line. Clearly it has negative slope, and it's probably not like -1, it's more like -0.5 or 0.3 or something. Let's try to figure this out. You know how to do implicit differentiation? It really is based on the chain rule. In fact, the chain rule that we just talked about, right? So what we do in differentiation, implicit differentiation is basically this. I can get my pen here. Differentiate with respect to x, right? So what we're doing is applying d dx to both the right and left-hand side. Okay, watch what happens. When you differentiate this with respect to x, you get 2x. And then if you must, you can write dx over dx because that's what it is, right? And the next one, it's going to be 6y, but remember, y is thought of as a function of x. So, I mean, this is more like this. This is what we are really seeing here, okay? So if you really want to pay attention to this and see what's going on, thinking of y as a function of x, if you differentiate this using the chain rule, you know, with respect to x, this becomes 6y times y prime, right? I'm not going to write y prime. I'm going to write this as dy over dx because that's what that is, right? And then plus 4, remember y becomes dy dx. Okay, the derivative of 8 with respect to x is of course 0 because that's a constant, all right? And so this is of course 1. So this becomes 2x plus 6y y prime plus 4y prime is equal to 0. I can capture all the y prime terms, which there are 2 of them, and then let's just move the other one into the other side, negative 2x, right? So y prime at any given point can be written this way, 6y plus 4 in the denominator, negative 2x on the top. Let x be 1 and y be 1. Remember, my vertical line means I evaluate this at this point. This becomes negative 2. And then you have 6 plus 4, which is negative 2 over 10. That's negative 1/5, which seems to be consistent with what we saw in the picture. Okay, so this is how you can do implicit differentiation. I think you have some equations, some formulas, or some problems that you have to do using this type of thing. Just for a one additional exercise, let me give you this, and then once I give you this question, you can pause this and try this on your own and come back and get the answer here. The equation is this: x squared plus 2 sine y minus e to the y is equal to 3. All right, find dy dx. That is the slope of the tangent line at the point 2, 0. Is 2, 0 on this graph? Yeah, you plug in 2 here, then you get 4 plus 2 times the sine of 0 minus e to the sine of 0. That's 1. Okay, so that number, I mean, the point 2, 0 is actually on the graph, right? And in case you're wondering, the graph, and you can, again, get your app, download an app, and then try to come up with your, your answer here. But it sort of looks, it's a very interesting graph. It's a graph, the set of all points satisfying this would look like this. This is the point we are looking for, okay? And try to find the slope of this. And let's see if you can come up with this on your own. Well, again, what you do is you take the derivative with respect to x of the entire equation, all right? And so this becomes 2x plus 2 cosine of y times y prime, okay? Minus e to the y becomes e to the y and y prime, right? And then 3 just becomes 0. Don't write 3 here, okay? That's a sort of typical common mistake because you just forget, that constant just becomes 0. All right, so 2 cosine y minus e to the y prime is equal to negative 2x. So the y prime is negative 2x all over. You probably notice here that the numerator, in fact, I'll just do this generally later. The numerator is always going to be the derivative with respect to x on the left-hand side. And then you have a negative sign of it. And then, so 2 cosine y minus e to the y, right? You evaluate this at 2, 0. The answer is negative 4. I hope you don't get 0 in the denominator. Well, actually, if you get the 0 in the denominator, that means it's a vertical line. The slope is, undefined, infinite. This is 2 times cosine of 0, that's 1, minus e to the 0th, which is 1. All right, so this is negative 4 divided by 1, and that's negative 4. And indeed, if you graph this by using your app or something, you can even calculate, or the computer or calculator or an app will help you find the derivative here at every single point. And if you put your cursor or the mouse at this point, it'll give you dy dx, which is exactly negative 4. Okay, so in general, this is what happens. If you have any kind of function like this, you have an expression of xy, which is equal to 0. Now, the thing is, this wasn't 0, but you can easily make this into an equation with 0 just by moving this on the other side, right? So every function or every graph of xy can be written in this way. Or maybe constant. I guess constant is okay. Okay. If you differentiate this, what you get is the partial of f with respect to x times dx plus, so what we are doing is we are differentiating with respect to x. And then you have the partial of f with respect to y, dy dx. Remember, this is the sort of like case number 1 of the chain rules we just learned, except instead of using t, I am using x, because clearly you can think of x as a function of x itself. And this is what's happening here. This is equal to 0, right? Now this is the y prime we are looking for. This is of course 1. All right, so this is fx plus fy times y prime is equal to 0, right? And this is exactly what happened in the 2 previous example problems. All right, so you can say y prime, which is dy dx, is simply negative fx divided by fy. And if you look at the previous 2 examples or 2 problems, you will see this is exactly what we came up with. Okay. Yeah, so use this in your homework, but most of your homework problems will have to do with applying either one of these chain rules, either case 1 or case 2 or case 3. All right, have fun doing your homework. And just to let you know, section 4.5 has been pretty simple. Section 4.6 is extremely, extremely important. Okay, it may be one of the most important sections, maybe the most important section in Calculus 3. We'll be talking about this thing called the gradient. Okay, and then the directional derivative. We finally will be able to answer questions like, on this surface, pick a point. What is the rate of change in a certain direction? Okay, but the gradient is probably the most important concept you will learn in Calculus 3, certainly one of the most important topics in multivariable calculus. So I hope you look forward to it. And until we go to that section, I hope you have a great day, great week. I'll talk to you later. Bye.